narrow that down.
No.
Okay.
No.
Okay.
Yeah, that's too much of a drastic change there.
Today my goal is to work on trying to bridge the algebra, which we've been mostly focusing on, and the graphical, which is now like, what do these functions look like in graphical form? And calm Joe's out. Yeah. So let's start with a bit of a review. You guys should have learned from me last year about quadratics, right? And you hopefully know the general shape of a quadratic is like the smiley face. It also, by the way, could be, the upside down one. Right. The other kind of function that hopefully you've learned of before is a linear function, a nice straight line function. We've also learned about things like the absolute value function, which is a v, those ones there. So my goal today is now to work on the characteristics of, well, we're going to start at the bottom. We're going to work with linears, quadratics again. But then we're going to talk about, well, what do cubics look like? What do quartics look like? What do quintics look like? And now, rather than doing the algebra side of things, now we're doing the graphical side of things. Most of the time, actually, kids actually like this because all the work that you do is in your graphing calculator, right? So when you're getting frustrated going, I can't factor this stupid thing, right? You use your graphing calculator and you use some of the tools in there. So, okay, anyways, I think most of these slides are actually pulled from like my previous courses. I just want to make sure you guys know the terminology I'm going to work with. Input would be like your x value. Have I talked with you guys about how an input is considered domain? No. So the x values that you input, you plug in as domain. The output is known as range. Just as a quick example, why don't we walk through the domain and range of these graphs we see here? What would the domain of this graph right here be? Yeah, that's often what it ends up being, because there's no reason that we can't use any number we want, because look, every number seems to be valid. Now that's not always true, by the way. In polynomial functions, most of the time it is, but I'm going to show you a graph that looks like this. This is a logarithmic graph, which we'll get to in another unit. Let's say I wanted you to find what's the output when x is negative 5. Well, if you went over here to negative 5 and looked for it, you'd be like, there's no graph there. Right? So I need you guys to be aware that although previously we've often said x is an element of the reals, that's not always true. We will show you more and more exceptions. Because that same thing is true here, right? You can have any x number from here to here, and really every x number here is also used as well, right? Same thing for range. Right here, every y value will eventually be accounted for. What about this quadratic function, though? Is that true? Where's the lowest point we have? Yeah, so we normally write it like this. Y is greater than or equal to negative 4. Because if I was looking for where it's equal to negative 5 or negative 6 or something like that, it never gets there, right? So sometimes what I suggest to kids to do, if they really don't understand this concept, is they get themselves a ruler. I'll just use this blue line as a ruler. And you go this way first, and basically run the ruler along the edge of like the paper here and say, okay, is every single x value as I go along there, was it covered? And like right here, that point's right there, so we're good. As I slide it over to here, there's a point right there. As I slide it over to here, there's a point right there. It looks like everything's covered, right? That's domain. Range would be if you took the same thing here, you flipped it like that, and then now you run it up and down. And if you do this graph right here, everything is accounted for. But if you do this graph right here, you actually get 2 answers. That's fine. We've learned in the past that's acceptable, right? But as you run it down like this, all of a sudden here, well, hang on, the graph doesn't touch that line. Is that clear? Cool. Okay, so we're using the same terminology. The other thing I bolded here is, do you guys know what I mean when I say standard form? Standard form, if it's not clear, is written like this. ax plus b, or ax squared plus bx plus c, or ax3 plus, okay. Standard form would be when it's FOILed. The opposite, perhaps, of standard form would be like factored form. Makes sense. But in general, like a standard form is FOIL everything out, right? And just write it just with as few terms as possible. Okay, and that's, I guess, what I was leading to on my next slide, apparently. The other way you could write it is factored form. One of the nice things about writing things in a factored format is that it's easy to know what your roots are. Right? Like if I were to give you x squared plus 6x plus 9, you might not know what your roots are immediately. But if I were to give you x plus 3, x plus 3, I know what my roots are. Negative 3. And only negative 3, right? Because it's there twice. So one of the things that you're going to be asked to do, I can nearly guarantee it, is you're going to be given a graph of a polynomial, and they're going to ask you for the equation of it. And we did this last year. The key to solving this is you have to know how to deal with the leading coefficient. Okay. What would the nature of the leading coefficient of this graph here be? That'll work. That's not what I was referring to, but I didn't guide you very well. That's the word I was looking for. Yeah. Yeah, good catch.
Oh, the graph.
Yeah, you're not wrong. The leading coefficient would be in front of the squared one, but it's negative. Here's how you might go about solving this. You might say, well, I know that we're going to have an equation in the form y equals, how about we'd say like x minus 4, right? Because clearly it has an intercept at 4, so x minus 4 is 1. The other intercept right here is just at 0, so I might just say the other one is like x. And what we're missing, though, is that leading coefficient. And so I taught you guys last year we write like an a in front, or we write some sort of letter in front as our unknown leading coefficient. Do you guys recall this at all?
Yeah.
You also need to know one other point on the graph. Fortunately for us, 2, 2 is on the graph. So we can plug 2 in right here, 2 right here, and 2 right here. Actually, that's not the right way of doing this, is it? Can't even do algebra right. Here, I'm sure you'll do this in a more organized way than I did, but I found a being negative a half. Does a negative make sense? Yeah, I mean, that's what I asked a second ago. The nature of the leading coefficient. You're looking at me funny, Darian. I lose you somewhere here?
Maybe. Wait.
You didn't get negative a half?
Oh, just kidding.
You're good now? Okay. The negative does make sense though, right? Because we knew that it was going to be a negative leading coefficient because the graph is upside down. But now we know the equation is going to be y equals negative a half x minus 4 and x. That would be a factored way of writing things. Does that make sense? One of the common ways that I've seen them assess on the diploma is they would give you a graph. They would then ask, what are the coefficients? They would make a numeric response. Because here's how they do that. If they were to give you an answer in multiple choice and they said like, you know, this one is this, which we said was the right answer. And then if they said another possible one was this, and they were to ask you which graph fits, a lot of kids, they would just type all 4 answers in their calculator, see which one matched, and they get it right. You get what I'm saying? So what they might do is they might say in standard form, written as ax squared plus bx plus c, what are the values of a, b, and c? See how that works? And then it means that you really can't reverse engineer and cheat. You would have to do what we did so far, which was find this equation right here, and then we'd have to FOIL it out. You get what I'm saying? So that's a skill I need us to be able to work on. And really, these two things, they go together because the graph ideas and the algebra ideas are really like the opposite sides of a coin, right? Like they're part of the same thing. It's just, it's 2 ways of approaching a function. A function can be written as an equation, but a function can also be written as a table of values and graphed. So anyways, that's my goal today, is to reconcile those. Okay, apparently that's actually what we just did. Okay. Does that make sense though? Okay, let's move on. Okay, so let's get to the point of my lesson now. So most of that really should have just been a review. Let's talk about what polynomials will look like. All of these things on the board here, by the way, are considered polynomials. Even 5. And this one drives a lot of kids crazy because they're like, hang on a sec, 5 is only 1, and I know the word poly means more than 1. But, I mean, here's another way of approaching it. You really have 0x to the 3, you have 0x squared, you have 0x, and you have 5. It is considered a polynomial, even though we don't write a lot of those things, right? And you could keep going. I could say, and I have 0x to the 4s, and I have 0x to the 100s, right? Well, not necessarily. What those guys over there are working on would be rationals, which would be like x squared plus 4 divided by x minus 2. That's not necessarily polynomial because these two things don't actually divide by each other. Remember doing this in one of our earlier lessons? If they divide nicely, it's polynomial. But if they don't divide and there's a remainder, it's not actually considered polynomial if it's like a fraction.
Oh, Lord.
Hello.
Graph.
No, he's actually teaching in Lazar. No, he's teaching in Wanzer. Okay. Rebecca, you actually asked a really good question there because there are some exceptions to polynomials. If I were to give you x to the minus 1, that's not considered polynomial because this is 1 over x, and now that's rational. If I were to give you x to the 1/2, that's actually rational, no. And if it's x to the 1/2, it's the square root of x, which is radical. So there's lots of categories of equations. You guys so far have mostly worked with polynomials. You should have a little bit of experience with square roots and fractions, but those things aren't considered polynomial. Does that make sense? So like the exponents basically have to be positive integers, right? You couldn't go to the power of 3.2, right? It has to go x to the 3, x to the 2, x to the 1. If it was x to the 5 over 3, it doesn't work. Okay, so I mean that actually ties in nicely to this little bit right here then.
Can you please
So,
call 3500? Kyle Blood, please call 3500.
Right? Your polynomials have to be whole number integers for what the exponents happen to be, from linears all the way up, basically. Right? So, okay, so here's some pictures of some basic graphs. Okay, and I want to use this slide just to kind of get some ideas of some patterns because you'll quickly pick up on the patterns. Okay. Here's a linear graph. And you'll notice that, like we learned in the past, it's very straight lined, right? Here's your quadratic graph, but it's not a straight line. It turned around. We had a name for this point right here. You guys remember what it was called? A vertex, yeah. Sometimes I'll use the word turning point, though. I know we didn't use it last year, but I might call this a turning point. I mean, because obviously it turns around, right? When you guys take calculus with me next semester, when take calculus, well, actually, you will. I'm not letting you not. Okay. Anyways, when we get to calculus next year, I'll show you how this is actually quite purposeful, these turning points. You'll notice that this one here does not turn around. This one turns around once. Well, this one turns around twice. And the pattern continues. This one turns around 1, 2, 3 times. This one turns around 1, 2, 3, 4 times. 1, 2, 3, 4, 5 times. So that's one of the cool things that you'll start noticing about polynomials is that the degree of the polynomial has one less turning point. So if it's a degree of 1 linear, it doesn't actually turn around ever. If it's a degree of 2, it turns around once. If it's a degree of 3, it turns around twice. You get that concept? And so that's one of the first things people notice is the number of times these things turn around. Here's another really key property. Take a look at the linear. The linear starts on the bottom and ends at the top. Opposite hemispheres, so to speak. But the quadratic starts at the bottom and ends at the bottom. The same hemisphere. The cubic, if I drew it all the way like continuously, would start at the top, this particular one, and end at the bottom. See how it goes across the map? But this would be a quartic, by the way, this is x to the 4. Starts at the top, ends at the top. Okay. So another thing that people start figuring out is that we actually can figure out the degree a little bit because it goes across the map or it kind of stays top and bottom. And in a way, can you see how this is kind of like a linear function? Except it kind of had like, rather than it being a straight line, it kind of went all over the place, right? But it's like it starts down here. It was supposed to end up there, and it just, on the way, it takes a few detours. And so what that means is that anything that's to the power of 1, 3, and 5 should always go across the grid. And everything to the power of 2, 4, and 6 should start and end on the same hemispheres. Yeah, if that's not clear, this is x to the 4 now, 5, and 6 as we go along. This particular diagram labeled on the bottom one. Now, how do we know whether it's going to go top to top or bottom to bottom? Not about that part, the leading coefficient. Because think of your quadratics. Why does this one go from bottom to bottom? Because it's got a negative leading coefficient. What would you surmise about this one right here, about its leading coefficient? Probably positive, right? Look at this one right here. It starts in the bottom and ends up in the top here. with like what's essentially a positive slope. Its leading coefficient is probably positive. This guy right here, because of its downhill general slope, probably has a negative leading coefficient. And once you start picking up on some of these patterns, graphing polynomials actually isn't all that bad. Like, it sounds horrible. Ugh, we have to learn cubics and quartics and quintics, but really, like, I could ask you to graph something to the power of 100, and it would suck, but you could, right? Because something to the power of 100 would have 99 turning points, and it's definitely going to start and end either top to top or bottom to bottom, right? I mean, obviously we wouldn't graph it, but you get the point. So, and that's I think what this next slide here I put on here to remind you of was just some of the words we use. Here's the leading coefficient. It controls the nature of like the graph, I think is a good word you'd use. Like the nature being like, is it top to top, bottom to bottom, downhill slope, uphill slope, right? That sort of thing. That's what a leading coefficient controls. All of the middle terms don't really do anything. But the constant term is actually useful for knowing some information. The first thing we did the last couple of days, constant term will help you figure out what factors could be. Right? Like if it ends with a 1, the only way we're going to be able to factor this is by like +1 or -1. That's the only way it will factor nicely. You know what I'm saying? The other thing is the constant term tells you the y-intercept. Nice, you guys were ahead of me. So you can also use that for the y-intercept as well. So now the higher the degree of the polynomial, the more x-intercept something could have. This is a slide from last year that I would have done when I taught you quadratics. You know how a quadratic can cross the axis and have 2 roots? The quadratic could literally just graze the axis and have 1 root, or it could not cross at all. That same concept really applies to all of these further graphs. Let me do a quick example here. Here's a cubic. I'm going to start it down here. I'm going to end it up here because cubics have to start and end in opposite quadrants. Here's a possibility. It could have just 1 root. That's possible. For example, this could be like x plus 1 and x squared minus 9x plus 1,000. The x minus 1 right here, it provides, well, that was actually a poor choice. Let's go with x minus 1. It provides a root right here of 1, and this quadratic piece left over, apparently it can't be solved, perhaps. You know what I'm saying? Because like if I tried to use the quadratic formula on it, it doesn't work, which explains why this little quadratic piece right here doesn't quite get high enough to actually like cross the axis. Okay, so that's one possibility. Another possibility would look like this. What if it just barely grazed and did that? This might look like this, x minus 1 and then x plus 1 squared. The x minus 1 is this one right here. That's the root of 1. And then over here, the negative 1 is right there. And it's squared, though, because it's like there's 2 of them. And that's why it just barely touches right there. Makes sense? Like we call it a double root. If I really wrote it out, it would be x minus 1, x plus 1, and then a second x plus 1. And see how this one counts twice? Because it counts twice, that's why it just barely grazes and just touches the surface there. Third possibility would be, what if it actually managed to come all the way up and keep going like this? Now you might have x plus 1, x plus 4, x minus 2. See how like this is your minus 4, this is your minus 1, there's your 2. So kind of like with a quadratic formula, the number of roots kind of just depends on how the graph tends to go. So you could have 1 x-intercept, 2 x-intercepts, 3 x-intercepts. We really don't know how many there could be. Does that make sense? Now I can tell you this. If the graph has to go across the map, I guarantee you there's at least 1 x-intercept. It would have to, right? So if it's a degree 1, 3, 5, or 7, and it's going across the map, I know it factors. I can't say factors, because maybe the answer is like some stupid irrational number. But I know that there's at least 1 root. Right? Whereas if it's quadratic or cubic, or quadratic or quartic, I mean, the graph could be this. See how that has no roots whatsoever? Right? And so, Joe, when you were getting frustrated earlier because you couldn't factor it, it's very possible that the quartic you were trying to factor is actually supposed to look like this, and it's not supposed to have any factors. Right? I mean, when you think of the probability, if I just gave you a random one, I mean, isn't it about just as likely that it looks like this as it is that it looks like this. This one has 4 roots, this one has none. So don't freak out if it doesn't factor, because that could be the point. Okay, anyways, so let's talk about some of these categories I just mentioned. The first one is the odd degree polynomials. These are the ones that are to the power of 1, 3, 5, 7, etc. We know that they go across the map, all the way across, which means that they must have domain and ranges that consist of everything. If it's going all the way across the hemispheres, then I guarantee you, every x and every y is possible. Is that logical? Okay, here's the black bolded word I should talk about, multiplicity. Multiplicity would be this example here, where, why did I draw this one? This is kind of a fun one. I have a couple of multiple roots here. This right here might be, say, x plus 2. This one right here might be x minus 1. And this one right here might be x minus 3. But do you see how this one here just barely touches? That means that it's probably because it was squared. And then this one went right through, so you only have one of them. And this one right here, how it barely touches, that's often because those things are squared. The terminology we use then is if it just does that, just barely grazes the axis, we call those multiple roots, or we use the word multiplicity. So this one right here has a multiplicity of 2. This one has a multiplicity of 1 because it went right through. And this one right here has a multiplicity of 2 as well. Ooh, good question. Because that's possible. Let me draw you one of those. Here, let me leave that on there for a second, though, just in case you want to draw that.
When it barely touches,
Yeah, like when it, you know how like when it just touches just the once, like that? Then that's typically because you have a multiple root of some kind. Okay, so name me for your question here. Multiplicity of 3 could look like this. It's going to go along. It's going to barely graze, but then it's going to keep going. Okay. It's almost as if you could zoom in right here, it's almost as if it wanted to go up, back, and like that. It's almost like it wanted to have a flip, but it chose not to, because literally right here, what's happening is you're getting x plus 1 3 times. Yeah, and so basically it like hovers over top of it and then keeps going. If you ever see one of those, it's probably a triple root. So if it just grazes and comes back, it's a double root. If it's like it was going to graze, but then it actually keeps going, it might be a triple root. So anyways, the word I need you to know is multiplicity. Quadruple will look like a 2 again, though, right? So like evens and odds will look very similar. So like in theory, you could have a quadruple root. And it would look, well, let me graph one here for you, since you asked. What if I were to graph this? Let's go with x minus 2 to the power of 4. And then why don't I throw one more on here? Times x plus 3. What would I expect to see? I'd expect to see a single root go through negative 3. And I'd expect it to just kiss the axis right at positive 2. Does that make sense? So if I were to graph this on a normal size, I'm hoping this shows up nicely. Here's where it went directly through one of them. And then here, it just barely touches. And honestly, this graph would have looked very similar if this wasn't to the power of 4, but it was to the power of 2. It's going to look almost the exact same. You get what I'm saying? But if it was to the power of 3, 3 is where it's just going to graze. See how it kind of grazes right here? But then keeps going. So just so you're aware, when you're factoring, it's very possible to get x plus 1 and then another x plus 1. It just means that it's touching the axis kind of twice. Anyways, that's odd. Even is like what quadratics look like. And so the biggest difference for even is that there is there's a high or low vertex kind of point on there. Like there is a point where the graph ultimately turns around, which means that the range is not everything. I guarantee that part, okay? Even if this was to the power of like 18 and it does this, right? Somewhere on here is a ultimate lowest or highest point. Okay, so don't make the range be everything. And then same thing again. You could have multiple roots again. Leading coefficients then tell you whether it's smiley or frowny, but you guys already know that. Here I've got some slides then just walking ourselves literally through each one all the way up. So even though the graph of y equals 2, because you kind of groaned at me when I was like, it is a polynomial, we're going to count that one first, right? So this would be the first one. It's a constant function where literally like it's x to the 0. Okay, think of your input machine. Right? In this graph right here, if we start with 1, it's 2. If we start with 2, it's 2. If we start with 3, it's 2. If we start with a million, it's 2. You know what I'm saying? So this is a really boring function because really, I don't care what x is. Whatever, you know what I'm saying? Like sometimes I'm flipping with my classes. I'm like, give me a number. No, it's 2. Give me a number. It turns into 2. Give me, you know what I'm saying here, right? Like, so constant functions, x is irrelevant. So if you do want to talk about properties though, every x is valid, I guess, because you can give me any x you want. I'm still going to tell you it's 2, right? But your range is literally just 2, right? Like there's only one output you'd ever get. So it means it's an even degree technically, because 0 would be, I guess, kind of an even number going on the pattern, right? 2, 4, 6, 8. But there won't be any x-intercepts with one exception. Maybe everything's an x-intercept. What would that graph be? Y equals 0. Yeah, y equals 0. Okay, so that's the first one. Then there's linear functions. So this would be like y equals mx plus b, or like this one right here would be y equals x to the 1 plus 0. Essentially, that's what this particular graph here is, right? Okay, by virtue of it being an odd degree, it's going to go all the way across the graph. So it has everything for domain and range, and it's going to have one x and one y intercept, right? This one happens to be the same one, but if I put that graph right here, like this, here's your x-intercept, here's your y-intercept. So, wait, quadratics. You can write quadratics a lot of different ways. This was in vertex form that you learned last year. Here I'm writing it in just your standard form. Again, every x is valid, but there is a minimum point for the range. So what I'm trying to say here is y is either greater than or less than some q value. I don't know what that number is, but there is a minimum point. This is the big one here. How many x-intercepts can you have then? You can't have more than 2 x-intercepts. Okay? The number of intercepts you have cannot be more than your degree. So if you're a degree of 2, you can only have 2 x-intercepts. If you're a degree of 3, you can only have 3. You might not use all of them, but that's your limit, right? So this is 1 x-intercept. This is 2 x-intercepts. That would be 1 x-intercept. That would be 0 x-intercepts. You guys follow that? By the way, you're always going to have a y-intercept. Always. Because how do you get a y-intercept? Y-intercept occurs when x is, unless there's some reason you can't plug in 0, you'll have a y-intercept. Does that make sense? And in these polynomial functions, why can't you plug in 0? Side note. What if that was your function? Try plugging in 0. I dare you. Try it. Try it. Yeah, you get what I'm saying here? So that's why this is a polynomial. Because really, this is x to the minus 1. I dare you. Right? You can't use 0 on this one. All right, moving on here. This is what cubics look like. I don't think I need to talk through every single slide one at a time because you guys could read them through, but do you feel like you've got kind of the concept here? Okay. Cubics, and then here's a slide just to kind of show how cubics could have 1, 2, or 3 roots. It really depends on how the function's written. And then here's quartics. Quartics look like this. I got to point one thing out about quartics. It is possible for a quartic to have kind of an oblong shape, and it might look something like this. Where, see how like this one went all the way down and then turned around? It is actually possible for it to do like just a little flip and then turn around. So sometimes quartics can look like a misshapen quadratic.
I saw that. That page where it says, are these rational expressions equivalent?
I have no idea why I asked that because they're clearly not.
They're totally not equivalent.
I don't even know why that's the question there. I would just simplify them, Scott.
Okay.
Yeah, because they're definitely not equivalent. Such a dumb question to ask. Okay. Sorry, I don't need to make sure I'm clear on that. You know how like the you could have that cubic that like just grazes the axis and kind of keeps going? That's possible with all sorts of shapes. So you don't actually have to have it turn around all the time. it is possible that it just kind of does like a little flip and keeps going. That also, like this would probably be quartic because this is like 1, and then here it's almost like it wanted to turn around, but like it didn't. It just kind of like just bent a little bit. So, and I can't give you hard and fast rules for everything, but these are just some general observations you'll see as you graph them. So, here's pictures of more stuff. So, okay, I threw this slide on here just to illustrate then that real world scenarios, sometimes we actually like can make a function out of it, right? Like a mountain range could actually be graphed with an equation now, right? I have a buddy who works for a GPS company, and like he does a whole bunch of geography tasks, and I don't fully know what he does, but I can totally see the idea of like as he posted on Facebook actually, he was taking GPS maps of the Waterton fire and like keeping track of where the boundaries were over time. Right? Now, granted, that's more circular, but you can almost imagine that like as you're making a wavy line, it might be his job to try to graph that or like to make an equation for it that fits that. Does that make sense? Yeah. So that you could then say, well, what if my latitude was, I don't know, just pick a number. What if my latitude was 7? Well, really, then he's just asking it for f of 7, right? And then that would tell you, oh, well, that's where the fire reached. You know what I'm saying? So like you can hopefully see that there is some overlap where this would be useful somewhere, because all sorts of shapes and things have curvy shapes to them. So, okay, so this slide here basically then consolidates everything we've done. Here's all the skills you have. You guys should know how to use the factor and remainder type theorems to use algebra skills. That should be one side of the coin. Can you algebra something? And that's mostly what I've made you do so far. Solving is also part of that. So like if I gave you x plus 1, x minus 2 equals 0, can you solve that? Okay, right. If I gave you x to the 3 plus 3x plus squared plus 3x plus 1 equals 0, could you solve that? It may not be fun, but you have the skills to, right? Okay. Well, there's other things I got to point out here. Don't forget you have quadratic formulas and you have factoring. Okay. This last one right here is kind of reminding you of some calculator skills you should know, though. You guys all have a calculator, right? Yeah. Okay. So if you go to your calculator, do you guys recall these buttons here? It's under second trace. Do you guys remember how to use value, 0, min, max, and intersect? Okay, let's talk through those. You know how when I give you, say, f of 3, f of 3 is asking you what happens when x is 3, right? That's essentially what your calculator is doing. Is if I were to find the value when x is 3, it'll find it for me on the graph. Right? Because all it's doing is your calculator is plugging 3 in for all your x's. 0, if you guys forgot how to, I'll do them all just because. 0 is your x-intercepts. And the way it works is you have to put your cursor on the left-hand side of where you think the intercept is, on the right-hand side of where the intercept is, and then it'll narrow down a search range to try to find where the intercept is. There, it was at 2. You guys remember that button? The next two are similar, max and min. You just have to know which one you're looking for. I'll use a minimum. I'm hoping that somewhere over here there's a minimum between this graph. You see how the graph is going way below the page right here? There. I'm going to go here. See how that's way over here now? See how like those 2 arrows are right there? This will now find the lowest point possible. Why would that be useful? What question might ask you for that lowest point? Find the range, yeah. And so if I did this, then the range is everything greater than negative 65, basically. Does that make sense? And then max is the opposite. What's intersect useful for? Yeah, if you have 2 equations, you want to find where they cross. That sometimes is useful. So here's a graph, and then I threw 5 on there. Here's how this would be helpful. If I gave you a function, I'm just going to write a random one, x squared plus 5x plus 7, and I want you to tell me where it's going to equal 7. Well, that's basically, well, here's the quadratic, here's 7, this is going to tell you where those locations happen to be. So that's how intersect can be useful, is to take two equations and find where they merge. Anyways, the point I want to make here is that don't forget now, in addition to all the algebra skills that we focused on these first 5 lessons, you have a graphing calculator. You can also use it to help you solve various problems. Right? So, as an example, Joe, you were working on like some sort of really hard cubic earlier, or quadratic, like quartic, right? And if I just made up random numbers here, let's say this one right here, maybe I can't factor it because honestly it can't be factored, not into nice whole numbers, but could it still have intercepts? Only the intercepts are like, 3.9732. Well, all you got to do is just use your graphing calculator and find the intercepts. So that's another possibility. Don't feel like you have to algebra everything. So, okay, let's try our last examples. I'm almost done here, right? Yeah. 3 examples real quick, and then let's do the word problem. Okay, let's try to graph this without our calculators, though, because you probably don't need your calculator to graph this one here. What kind of graph is it in terms of its degree? Cubic, right? It clearly has 3 roots, right? There's one at 1, there's one at -2 and -3. Where's the y-intercept going to be? Yeah, how'd you figure that out? Yeah, I mean, I wouldn't even multiply the whole thing out. I would just do just a part of it. Eventually, -1 will times by 2, which will times by 3, and that's -6. So I now know 4 points on the graph just by just looking at it. A root of -2, a root of -3, a root of 1, and a y-intercept of -6. The only other thing I got to do is really connect the dots. Right? I just have to make sure I connect them in the right order, though, because there's 2 ways you could maybe try to do this. Let me do a wrong way first. I could try to do maybe like that. But it has to be cubic, and this is not cubic, and it also has to have a positive leading coefficient. So if it has a positive leading coefficient, it needs to have like an uphill trajectory. So I might do like, it needs to start here, it needs to end up here. So it looks like it probably is going to look something like that, give or take. And I mean, if you have to use your graphing calculator, go ahead, but the goal here is to try to just know what it's going to look like without it. Okay, so let's not write them down. Let's just talk through them. What are the roots? -3, -2, and 1. What's the y-intercept? -6. And then general end behavior. If this ever comes up, you guys know your quadrants, right? This is quadrant 1, and this is quadrant 3, yeah. I've seen them do this on numeric response. They might ask you which quadrants do they begin and terminate in, or something like that. And then it might be numeric response. So then 1 and 3 would be the ones you'd use, or 3 and 1 maybe. Yeah, it starts here and it goes around this way. Yeah, so 1, 2, 3, 4. Let's try another one here. Let's try to graph this one as best we can without using a calculator first. And then we use the calculator in a second. Sorry. Okay, it's cubic. How many roots could a cubic have? Could have 3, 2, or 1. Can it have 0 though? It can't have 0 because we know it has to go across the axes, right? So this one's a negative, so I'm going to kind of start it up over here. So that gets me started. And I do know the y-intercept is at -4. So don't draw this, but here's now our question. Does it look like this? Like that, perhaps? Is it that sort of shape? Where there's, say, like 1, 2, 3 roots? Oh, that's a possibility. Apparently this is a lot slower than I wanted it to be. Okay. Now we could graph this, but I want to do one thing before we get to that. Why don't we do a quick check and see whether the factor theorem works? Because there's not a lot of numbers that go into 4, right? Really, it's 1s, 2s, and 4s. So here's how I might try this. Just to avoid the calculator. I mean, the calculator will work, but I might go -2 bracket, let's go -1 cubed plus 6 minus 1, minus 4. Why am I doing it in this section though? That's dumb. Okay. Minus 2, bracket, minus 1 cubed, plus 6, minus 1, minus 4. That didn't work. Has anybody else tried any other ones yet? 1 worked? Sweet. Okay. So if 1 worked, you guys know what I mean. Once you find 1, just stop, right? So if 1 works, first of all, that means that 1 is my intercept then, right? If 1 works, 1 is my intercept. And to help figure this out, x minus 1 was a factor. Then, sorry that this is not exactly in the greatest spot to work from. Okay, you're going to want to go minus 2, 6, and minus 4. Good, someone said it. Don't forget to include 0 for the x squared. Because I know it's not written there, but there are 0 of them. Right? And then do your synthetic, right? Minus 2, 2, minus 2, 2, 4, minus 4, 0. Sweet. So then you should be left with negative 2x squared minus 2x plus 4. That makes sense to everybody? Alright, this one right here, it's kind of gross. But we could take a stab at trying to factor it, I guess. You know what I would do, though? I would factor out a negative 2. Does that make sense? Factor out a negative 2. So I'm going to pull the negative 2 way out to the front. And if that happens, I'm left with x squared plus x minus 2. Yeah. You guys all able to follow that step there? Now it's so much easier to see, because this does factor, right? This factors into a plus 2 and a minus 1. Okay, so again, without using my calculator now, I should know a little bit about its properties. We knew there was going to be a root at 1. Where's the other root? Negative 2. So let's put that over here. Negative 2. What's special about the root at 1, though? Multiple. Yeah, it's a multiple root, or it has a multiplicity, which means that when I fill it in, it's just going to graze the axis. So now let's fill in the blanks. It seems like this should probably go down through the 2, through the minus 4. If it tried to go through the 1 the rest of the way up here, that wouldn't finish where we want it to, though, right? Because we know it needs to finish down here in this quadrant. So it's just going to graze the 1 and then go down there. Does that make sense? And I mean, if you wanted to, you guys are going to have more graphing questions, I believe, on your next assignment. I mean, you could graph it real quick. Just double check. But I do want to really encourage you, try to be able to do the algebra skills and the graphing skills. Try them both. Oh, yeah, that seems to fit more or less what I thought it was going to be. All right, I got 10 minutes, 2 examples. We got this. Negative x to the 3 plus 13x plus 12. So if we want to do this algebraically, let's start with the 12, I guess, right? Let's see if there's anything. I mean, 12's got a lot of possibilities. We just need to find one. Negative. I always do negatives first just because they require an extra symbol. That's just me, though. No, sorry. No, I haven't even made a key for it because it's slightly modified. Can you guys just keep working and see if you find one that works? Oh, okay. Okay. How about this? Can you guys try to factor this while I look at that then? With 6 is the answer? So only 6. Okay. So you know how if you had a quadratic with, like, say, x equals 5 and x equals 3, you'd go x minus 5, x minus 3, and you just FOIL it, right? If you only want one answer, do this. If x has to be equal to, say, 7, go x minus 7 here. Also go x minus 7 here. Just use the same number twice. That makes sense. Now, if you only wrote it once, That's not quadratic, right? Yeah, so just write it next to itself. It is. It's sneaky. There's a lot of good learning out of that one, though, right? Like you have an aha moment. Do you guys manage to factor this thing all the way? Okay. So what did you say worked? One worked? Negative 3. Okay. So negative 3. So if I do x plus 3, negative 1, 0, 13, 12, negative 1, negative 3, 3, 9, 4, 12, 0. So we've got x plus 3, negative x squared plus 3x plus 4. I don't know about you guys, but I would have factored that negative out just because I hate having negative leading coefficients. And I just would have flipped all the signs. I don't know if you guys did something like this, but if you had that negative x squared there, I just factored in front. And then you'd have x plus 3, this will be x minus 4, and x plus 1. Did you get to that by the time you were done factoring everything? In a different order, maybe? Do you have like a negative x plus 4, maybe? But then how does that account? You need a negative as the front one of them, right? So one of them would have to be a negative x something, right? Because you had a negative out here, right?
I got it wrong first.
So this is negative 1 right here, right? So when you factor this right here, this guy right here, these two pieces right here, they won't provide you the negative x squared you need. You know what I'm saying? Because this x times this x won't give you the negative x squared. So this would have to be like say negative x plus 1 or negative x minus 1. I find the better way of doing it is to factor their negative in front, pull that out in front, and then you have x squared minus 3x minus 4. And then that solves your problem.
I have multiple times to do this.
Well, let me just graph this out real quick here. You're going to have a y-intercept up here of 12. You're going to have an x-intercept of negative 1, negative 3, positive 4, and with a negative slope kind of to it, it would look roughly like this. Okay. Well, the negative just is what gives it the negative inflection to it, right? Right? So that's what the negative tells you, is that it better be going downhill. If it wasn't a negative, then it would have looked like, I don't actually know how that would have fit together. Okay. Okay, one last thing. They might not ask you about Rice Krispies, but they might ask you a word problem. Okay? And this is a really common type of word problem, only it's stupid because I just made it a Rice Krispie square. But can you guys picture like a cube like this? Here's a Rice Krispie cube. And originally the dimensions were supposed to be, for this cube, were supposed to be 1 by 2 by 5. Well, whatever. It's a Rice Krispie prism, whatever. Okay, you guys okay with this part so far? Stay with me. I know we're almost done. Okay. What we're going to do here is we're going to remove the same amount from every dimension. Thank you. Here's what that means then. If it was a 1 by 2 by 5, well, what ends up happening is you're going to take an unknown amount off of this dimension. You're going to take an unknown amount off of this dimension. And you're going to take an unknown amount off of this dimension. But it's the same amount off all three sides, right? Okay. And then here's the cool part is they tell you that when you're done, you want to have 6 feet left. So what they're really implying in this really silly question, but the concept is what's important, is that if you were to take 1 minus x, the length, multiply by the width, and multiply by the height, when we're done, we want to have 6. How do we solve this? I wouldn't. I would use my graphing calculator. Right? Which I think is the point I want to make at the end of this.
Cleaver, Frank, Bo Frank, Jason Clayton, Haley Servo, Brady Anseller, Sarah Foot, Neil Shade. Please come to the office. Oh, and Ryan Burrows. Please come to the office.
Okay, so I'm going to type in this thing. This is going to be a cubic, correct? Because clearly there's 3 factors to it. We're going to make it equal to 6, and then all I've got to do is go to my graph and see where they cross. Now, here's the problem. It actually crosses in more than one spot. It clearly crosses right here and right here. So I'm going to try to intersect to try to find those. Well, let's talk through that in a second here. I'm going to try to find the first one, which is, let's see, somewhere around here. I've got an x value of about 0.267. Okay. Well, whatever it rounds to, yeah. I didn't round it properly. Can you guys get that first one that's just right there? Oh, okay, so I've got 1 minus x, 2 minus x, 5 minus x, and then I want it to equal 6 on a second line. And then I intersected. Okay. Okay, now see how it crosses over here another time though? It looks like it crosses over here at 4. Okay, so a couple of thoughts here. First of all, do you guys possess the skills to be able to kind of write an equation and solve for x? Okay, why are we getting more than one x? Well, cubics maybe cross more than one spot, but there's only one answer because one of them is extraneous. Which one shouldn't count?
4.
Why?
Because you can't go into the negatives of the amount of fractions you have.
Yeah, right? Because if you're starting with 1 foot on one side or whatever I picked the 1 to be, you can't take 1 minus 4 in the real world, right? Like, that's not logical. Now, the reason why it works, why did we get an extra answer? Well, 1 minus 4 would give you a negative number, right? 2 minus 4 would give you a second negative number. What do 2 negatives do when you multiply them by each other? Gives you back a positive. You know what I'm saying? So we picked up I lost you on this? 1 minus 4, 2 minus 4, and 5 minus 4 does actually equal 6. 1 minus 4 would give you negative 3. Now, we know in the real world you can't have negative 3 length, right? This one would have given you a negative 2 length. But you know what ends up happening is your negative, which is not logical, and your second negative, which is also not logical, would have multiplied by each other and given you a positive answer. You know what I'm saying? So clearly 4 is not right. So there's actually only one answer, this one right here. So this actually helps me show 2 points. If you get a word problem, you need to be able to kind of write your own equations to solve it. And 2, you guys remember this term extraneous, right? Like non-logical answers, answers that are like phantom answers that crop up where it's like...
I didn't get 100 on the test last year.
Okay.
What'd you do?
All right. Anyways, other than this one here.
Two wrong to make a right. My name is Marissa, and I'm actually smarter, but nobody really pays attention.
Sorry.
I'm not too bad.
There a little bit. Because you know what it just goes over. Okay. For anyone who's not done the assignment, I'll just leave the keys up for a couple more days because I rearranged where your time was at. So, do you guys want to move on tomorrow still too, or you want to work day tomorrow?
Up to you.
Okay, let's figure it out tomorrow. See where you guys are at.